In this lecture, we look at graphs of functions focusing on piecewise functions. Functions need not be described by an equation. Some, like the function color we described in section 1.1, will not involve equations at all. Other functions can be described not by a single formula, but by a collection of them. A piecewise function is a function which is described for pieces of the real line. It will obey one rule in one region and another rule in another region. One of the simplest such functions might be described by the question, how much does it cost to mail a letter? Let us assume that we're mailing a letter that weighs less than 4 ounces, and the U.S. Postal Service, as of 2013, offers a price chart, which is copied on the next slide. Here's the price chart for the cost of mailing an envelope. Notice that if we are mailing an envelope that does not weigh over 1 ounce, then the cost is $0.45, in other words, 45 cents. If the envelope is between 1 and 2 ounces, the cost is 65 cents. If it's between 2 and 3 ounces, the cost is 85 cents. If the envelope is between 3 and 3.5 ounces, the cost is $1.05. And after that, we start using large envelopes and have to move to another column. So as we said, these tell us about the value of mailing an envelope between 0 and 1 ounce, between 1 and 2 ounces, between 2 and 3 ounces, and so on. So we have 4 different pieces in the first 4 rows. And then after 3.5 ounces in weight, but less than 4, we end up costing $1.50. We can describe this cost of first class function as follows. F of x, the output, the cost, will be 45 cents if x is between 0 and 1. But if x is between 1 and 2 in our second line, then the cost will be 65 cents. If x is between 2 and 3, the cost in cents is 85 cents, and so on. The graph will look like this graph below. If we plug in on the x value anything between 0 and 1, we are discussing an envelope weighing less than 1 ounce, and so the cost will be y equals 45. And so it will be represented by the blue line above. So that's an example of a piecewise function. Here's another example. Consider the function defined in pieces as follows. If x is less than or equal to 0, then the output is 2x plus 1. But if x is greater than 0, the output is x squared plus 1. Let's compute f of 2, f of 0, and f of minus 2, and then graph this function. Now, if x is less than or equal to 0, the function obeys the first rule, f of x is 2x plus 1. So f of minus 2 is 2 times minus 2 plus 1, or minus 3. And f of 0 obeys that rule. It's twice 0 plus 1, which is equal to 1. If we plug in minus 2 or 0, we obey the first rule. The output is 2x plus 1. But if x is positive, then we have a different rule. The second line, the output is now x squared plus 1. So when we plug in 2, for example, we will square 2 and add 1 and get 5. If we graph the function, it looks like this. On the left of x equals 0, we have the line y equals 2x plus 1. And on the right of x equals 0, we have the parabola y equals x squared plus 1. Notice how these two pieces are glued together. We can see the line y equals 2x plus 1 in the region where x is negative, and we can see the parabola in the region to the right of the y-axis. Let's do several more examples. Here we have the function where the output is 2x plus 2 if the input is less than or equal to 1, and the output is just a constant 4 if x is greater than 1. We're told to compute f of 0, f of 1, f of 2, and f of 100. So let's plot some points. If x is 0, we're obeying the first rule. X equals 0 and x equals 1 both fall in the region where x is less than or equal to 1, so we obey the first rule. So f of 0 is twice 0 plus 2, and f of 1 is twice 1 plus 2. Since x equals 2 and x equals 100 both fall in the region where x is greater than 1, then we obey the second rule, so the output is 4 in both cases. Here's the picture. To the left of x equals 1, we have this line where y is 2x plus 2. But to the right of x equals 1, we have the constant or horizontal line where y is 4. One more example, this one's fairly complicated. Here we have 5 pieces. If x is less than or equal to 0, the output is x squared. But if x is between 0 and 1, the output is 0. If x is between 1 and 2, the output is 1. If x is between 2 and 3, the output is 2. But if x is greater than or equal to 3, the output is x. We can compute some function values for practice. If we plug in minus 1, we obey the first rule, so we have to square minus 1 and get 1. If we plug in 0.5, however, we obey the second rule, and we'll just get 0. If we plug in 1.5, we obey the third rule. If we plug in 2.5, we obey the fourth rule. And if we plug in 3.5, we obey the last rule. So we can plot these points and talk about what happens in the various regions. Notice that in the first rule, we're going to get a parabola where y is equal to x squared if x is less than or equal to 0. In the case of the second rule, we'll get a horizontal line where y is equal to 0. In the third rule, when x falls between 1 and 2, we'll get a horizontal line where y is equal to 1. In the fourth case, we will get a horizontal line where y is 2. And in the final case, we'll get a slanted line where y is equal to x. So the graph of that looks like this. You see the parabola to the left, suddenly ending in a horizontal line at the bottom where y is equal to 0, and then we have several step functions, and then finally we have this slanted line where y is equal to x. Note the use of closed dark circles, black circles, to indicate that a point, such as 1, 1, is on the graph, and the use of the light open circles to indicate that a point, such as 1, 0, or 2, 1, is not on the graph. If I plug in the value x equals 2, for example, the output is y equals 2, up where the black point 2, 2 occurs. It is not at the point 2, 1. That open circle indicates that when you plug in 2, you do not get the output of 1.